In this video, I'm going to be talking about continuous functions, what it means to be continuous. I'm going to talk about the intermediate value theorem. I'm going to do a couple of example problems also. All right, so I'm just going to first start with an example of some discontinuous functions that you're familiar with. And we'll use our kind of intuition about what we know about discontinuity to figure out what it really does mean to be continuous. Okay. So we know that in the past, we've defined continuity as like a function's continuous if you can draw a picture of it without lifting the pencil up off the paper, which is actually a pretty good definition. There are a variety of definitions for continuity in a variety of different courses, and some of them are really unwieldy to work with. And then, actually, if you go far enough, you can start to look at it from a different perspective and see that it maybe actually is not as nasty as it is in, say, an introductory real analysis course. But let me just draw you a picture of a function that is discontinuous, right? Because I have to pick up my pencil to draw it. We've got like a jump discontinuity. Okay. Now, so far in this course, we've said that, the limit as x approaches c, if this is x equals c, the limit as x approaches c of this function does not exist because of disagreement in one-sided limits. Also, if we had like a vertical asymptote or something, that's a situation that would also be discontinuous, right? Say maybe we had 1 over x minus c squared. I always like that one because both of the arms go up. Okay. This is discontinuous because I have to draw one piece and then I have to draw the second piece. It's two different pieces. Okay. And then there's something that maybe if you remember from pre-cal, you called a removable discontinuity. That was a hole in the graph. Right? Okay. And so far in this class, we've been talking about this case quite a bit, where we've got a hole in the graph and the actual value of the function is elsewhere. Right? We could say that maybe the limit of this function as x approaches c is looking like 2, but f of c is looking like 3. Okay? And this is discontinuous because if I was going to, you can draw with a hole without lifting your pencil up, but if you were actually going to respect the fact that there's nothing there at that very corner point, you'd have to stop and then start again right after it. Okay? And that is a discontinuity. Now, we say removable because if we just remove this spot from consideration, the function's otherwise continuous, right? It looks really smooth. And so the thought is that this is really close to being continuous. And this would be continuous if we could just take this and put it there, right? If that circle was filled in, this function would be continuous. And so that would be if the limit of the function equaled the value of the function. And that's the definition of continuity we're going to take in this class. Okay, so we're going to say f of x is continuous at x equals c if the limit of f as x approaches c is the same as f of c. Okay. Right? Because if we have the limit and it's not equal to the value of the function, we have a discontinuity. Okay. If the function is not even defined, then we don't even have a chance to be continuous. Okay. Here, the limit doesn't exist, okay, so it can't equal the value of the function. And just, kind of a remark about that this is a, relatively weak definition of continuity, and it depends on our definition of a limit, which is also not particularly rigorous in this course, but we don't really need it. We need the idea of the limit to be able to answer questions about the concept. We don't need to prove that a limit exists or prove that a function is continuous using epsilons and deltas, at least not in AP calculus. All right, now the first example is definitely the type of problem that I used to like to ask when I taught classes like pre-cal, algebra 2, college algebra, and we studied piecewise defined functions. So you may have seen this type of problem before. And so the question is, what value of k makes this function a continuous function. And I kind of want to draw a picture of it for you. Okay, so x squared minus 3x plus 9 is going to be an upward facing parabola. I'm not going to draw you like an accurate graph of this, but it's going to be fixed, right? We know what the graph of this thing looks like. And at x equals 2, as we're, it goes all the way up to x equals 2, we know that the vertex of this thing is going to be negative b over 2a. So it's going to be negative or positive 1.5. So I know that the parabola is going to kind of look like this. It's going to go down and it's going to hit its bottom at 1.5, and then at 2, which I know should be after it, but I don't know really when after, and when doesn't exactly matter, is here. And then I've got this function that has a fixed y-intercept but a variable slope. But I'm just going to say, maybe it comes through here. What we need to do is we need to manipulate this k so that it's going to actually pass through here. Okay? So that this thing, and if you view these as like movable pieces, we need to manipulate this k so that we can move this to meet up with that point. And so what form that takes algebraically is that we need x squared minus 3x plus 9 to equal kx plus 1 at the x equals 2. Okay, and that will mean I'm going to plug in x equals 2, so I've got 4 minus 3 times 2 is 6 plus 9 is equal to k times 2 is 2k plus 1. And then I'm going to actually do this. This is 13 minus 6 is 7 minus 1 is 6, leading me to believe that k is going to need to equal 3. And this is most often a multiple choice question. Okay, it's a very typical AP calculus question. Now here's one I've got that I want you to try on your own. And this is going to be, this one's going to be a little more involved algebraically, but I think it would be good practice for you. So I've got a function g of x that I'm going to copy down over here. I meant to copy this before I started recording, but it's all right. It's going to be x minus 4, ax plus b, and x plus 2. And the domains of each of these pieces is x less than negative 2, x between negative 2 and 1. Whoops, an x there. And this being x bigger than 1. All right. Now I want you to try to do the same thing, except this is going to require you to solve a system. Now, I oftentimes say that Algebra 1 comes up all the time in AP Calculus. If you actually look back at that equation that we were solving for k, it was actually a pretty simple equation. And if you look at what's going to happen to this when you plug in, you equate these and plug in negative 2 and equate these and plug in 1, you're going to end up with two equations with variables a and b, and you're going to solve it just like you did in Algebra 1. So I'm going to let you try this on your own, and then in about 5-10 seconds the answer is just going to pop up on the screen, and you can check your work. So you would definitely want to pause the video now. Alright, there you go. So first I set the first two pieces equal to each other and plugged in x equals negative 2, giving me negative 6 equals negative 2a plus b. And then I set the second and third pieces equal to each other and plugged in 1, right, getting 3 equals a plus b. And then I solved the system. Okay, I wrote the first equation and the second equation. I subtracted the second equation from the first equation because I saw those b's and I kind of wanted to eliminate on that. You could have doubled the second equation and added it to eliminate on a, and then you would have just gotten b equals 0 first, and then you would have concluded that a was 3 after that. It doesn't really matter because you're going to end up with a equals 3 and b equals 0. All right, and this is kind of the last one of these examples that I've got, and I don't like this problem very much, but I have seen it as a multiple choice item on some of the AP Calculus multiple choice tests in the past. And I'll tell you why I don't like it in a second, but it says that h is a continuous function with h given by this fraction for x not equal to -7. And you can look at it and you're like, okay, I know what I'm supposed to do. I'm supposed to factor that and cancel some stuff, because you see a difference of 2 squares. That should set off an alarm bell in your mind. You've been through enough algebra-based math classes that you see the difference of 2 squares and you know you're supposed to factor. So really what h is x plus 7, x minus 7 divided by x plus 7. Well, that means that it's x minus 7 unless x is equal to -7, where it's undefined. So there's a hole at -7. But if it's continuous, then it's just going to, we're going to fill in that hole just like I was saying. If it's a line with a hole in it, but we know it's continuous, so we need to make sure that it's like that, well then why wouldn't we just say y equals x minus 7 in the first place? It's just kind of redundant. Like, why? There's no reason a person would want to write that unless they needed there to be a hole there. But if it's continuous, then there isn't a hole there. So that's why I'm not like the hugest fan of this type of question. But it is definitely something that you could be asked, and I've seen this type of question before, so I want you to be aware of it. All right, and then I realized something else that I probably should mention is, types of discontinuities, because this is language that can show up on the exam and on my tests and quizzes, and I just want to make sure that we're all using the same, terminology. And so we've got removable. There's really 2 types of discontinuities. There's removable and non-removable, and there's all sorts of different synonyms for this. There's removable and essential. Some people call these singularities, not discontinuities, but that's more for a different type of function. But a removable discontinuity is a hole in the graph. Okay, and the key aspect of this is that the limit exists, but is not equal to the value of the function. So, limit as x approaches c of f of x exists, but it's not equal to f of c. I'm just going to slide that over there. Okay, and then there's non-removable, and that can kind of get broken down into a couple of different cases, right? Because we have at least 2 types. Okay, first would be because of a vertical asymptote. Sometimes called an infinite discontinuity. Okay, and you know what that looks like. This would be where f of c doesn't exist, and the limit of f as x approaches c don't exist. Okay, we need them to both exist and be equal in order for the function to be continuous. Okay, and I guess I can draw you a picture of that. Got one right here. It's like that. I don't know, something fun. And it's a vertical asymptote. The function doesn't exist. And then we've also got a jump discontinuity. And that's f of c doesn't necessarily not exist, but I know for a fact that the limit won't exist in that case. So that's like kind of the hallmark of a jump discontinuity. And it is certainly possible that f of c would not exist at a jump discontinuity. You think about that new function to us, f of x equals absolute value of x over x, or x over the absolute value of x. That function isn't defined at its jump discontinuity, but it still has one. Okay? And it's certainly discontinuous. Okay, I will just mention that, a function like sine of 1 over x is definitely discontinuous at x equals 0, because there's not a limit of sine of 1 over x as x is approaching 0 from either side because of the oscillation. Okay, but I'm not even going to mention that because it's not relevant to us. All right, and the last kind of idea I've got for you today is the intermediate value theorem. And so I didn't state it as rigorously as I would for a different type of class, but if we've got a continuous function on an interval, and maybe I'll draw you a picture of this going on. So I've got some sort of interval a to b. Say a is over here, and b is over there. And I've got a function that's continuous, and maybe it's this is f of a, and maybe over the course of time f increased, and f of b is up here. Okay, if we've got some value, some y value between f of a and f of b, like say this y value, whatever it is, y0 I said, then there has to be a place. If the function is continuous, I know I can draw a picture of it in one go. So I have to be able to draw it in one stroke of the pencil and get all the way up to f of b. And I can avoid it for as long as I want, but since this is a function and it's continuous, I'm going to eventually have to cross, right? There's no way around it. It can happen sooner, it can happen later, it can happen multiple times. Okay, but I know it happens at least once for some x value in here. Okay. Also could be stated, I'm going to draw you, let's just suppose this is like Texas coast, and then I think it kind of like that's Louisiana, and it like it comes over there, and then Florida comes way down. And suppose I wanted to drive to Miami, okay? And we know that there's not a bridge from Texas to Miami. And you also know that somewhere around here, around Louisiana and Mississippi, is the Mississippi River. And maybe I'll draw it like really exaggerated. Say here I am in Austin, and I'm trying to drive to Miami. Okay. Now this is definitely a more than one variable situation, but say I've got the river here, and it's like and I'm not going to drive all the way up to wherever that water comes from and try to drive all around it. I'm not even sure if that's possible. You'd have to ask a geography teacher, but I'm pretty sure that you could drive far enough north that you could drive around the Mississippi River. But I'm not going to do that, right? I'm trying to go to Miami. And you know that at some time, if I started here and I drove on the roads, didn't go out here, that I had to cross the Mississippi River. There was some time when I was right over it. Okay, that's the same idea. So that in order to go from here to there, maybe I went across Houston, Louisiana, and I crossed on that bridge. I did that not even that long ago. Or maybe I went up a little higher and I went through Tennessee along the way. I don't know. I know some people in Memphis. Either way, I'm going to be crossing the Mississippi River at some point. There would be some time, as long as I drove continuously, as long as I didn't do some sort of vanishing act and then all of a sudden reappear over here. That would be very discontinuous. Okay. I think that's all I've got to say about it. I'm going to show you some example problems, but that'll be it. Now, most of the actual multiple choice and free response problems on the intermediate value theorem require a little bit more calculus knowledge. They need more context. They might need you to understand the concept of the derivative, because they're going to try to confuse you about the difference between the intermediate value theorem and other theorems we're going to learn in this class. But there are some table problems that are very direct intermediate value theorem questions. And so there are ones like this. If f is a continuous function, with tables or with values given in the table above, what's the minimum possible number of x-intercepts on its graph? Okay, and an x-intercept, it's like a 0 or a root. It's a place where f of x equals 0. So I can see already at least one time. But if it's continuous and it goes from negative to positive, it has to pass through 0. Okay, it could pass through 0 more than once. It could go from -2 positive at 1, negative at 2, back to positive at 3, right? There could be more. I'm talking about the minimum possible number. So I've got one here, for sure. I've got another one here, because I see it going from positive to negative. Okay, I don't know that there are any more anywhere else. Okay, and then I also know that there's going to be one at least here, between -1 and positive 1/2. Okay, so I would conclude that there are at least 3 x-intercepts. And if you wanted to draw a picture of this, you could actually plot this, on a piece of grid paper or something, and then you would find that if you connected the dots with like just lines, which is kind of like the minimal function, then you would also get 3 x-intercepts. Okay. That's definitely an option. Okay, so I'll show you another example. All right, last example I've got, and this is based on a multiple choice question, but I'm showing you how I could make this a little more challenging by, making it an open response question. Here you've got a table of values, and you know that f is a continuous function. And I'm going to ask you, what are all the possible values of b that guarantee 2 solutions to the equation f of x equals 1 on the interval 0 to 2? Okay. So what I'm actually going to draw you a picture of this one to explain why the answer is what it is. So I'll tell you that a possible value of b would be 0, right? Because if it goes from 3 down to 0 and then back up to 5, it's got to cross 1 from 3 to 0 and from 0 to 5. And as it turns out, any value of b that is strictly less than 1 will also guarantee 2 solutions. If b was equal to 1, then that would only guarantee 1, because maybe it went from 3 down to 1, and 1 was the minimum, and then it went back up to 5. Okay, so I'll draw you this. I think I'm going to make this... No, I can do that. Just enough for... Okay, so 0, 1, 2. Okay, so I really don't... Maybe I'll actually space this out, and I'll say this is 1, and that's 2. So that's barely, not really, though. Stretch that a little bit. Cool. Okay. Now what I'm going to do is I'm going to actually plot. So 0 is 3, 2 is 5. Okay, and I want 2 solutions to the equation f of x equals 1. So I need to cross this line twice, and if I only had b was equal to 1, it might go down and then just back up, and that would only be 1 solution. And if I had b bigger than 1, I am not guaranteed any solutions. But any b less than 1, if I'm anywhere down here, even right here, I've got to cross here, and then I've got to cross again to get back to 5. So any value of b that is less than 1. And that's all I got for you for this video.